So we're going to start talking now about electromagnetic radiation and spectra associated with that electromagnetic radiation. Some people typically call electromagnetic radiation light, but visible light is what people think of most when they deal with electromagnetic radiation. But that's only a small portion of the electromagnetic radiation out there. Now, when you think about electromagnetic radiation, one thing to keep in mind with the name, electromagnetic, basically it means we're dealing with radiation that has an electric field associated with it and a magnetic field associated with it. Alright, and we're going to relate that to the atom. One of the most important things in the atom dealing with this is going to be the electron. So when we think about the electron, electrons are extremely small. If we look at a single speck of dust, that single speck of dust is going to have more electrons in it than the number of people who have ever lived on the Earth. Keep in mind that Avogadro's number concept, right? That 1 mole is equal to 6.022 times 10 to the 23rd numbers of things. So because electrons are so small, we have lots and lots of them around. Because electrons are so small, though, we're going to have to think about what's happening with them differently. Now, the behavior of that electron in an atom is going to be very important to the behavior of the overall atom. Okay, if we think about ionic compounds, what happens with ionic compounds? Why do they form the ions that they do? Well, it's loss of electrons, gain of electrons. It comes down to those electrons. So when we consider this atom and we want to deal with these electrons because they're going to help us describe the behavior of atoms, we come across a problem. We can't observe an electron directly. All right, we can't actually go in with our physical eye and look at it. And any measurements that we do on it, those measurements are going to cause us to change the electron's behavior, something called the Heisenberg uncertainty principle. All right, so whenever we do a measurement on an electron, we change its behavior. Okay, so we can't measure it directly. We can, however, observe it indirectly. All right, let's look at a couple examples of these. First one is the pickle light. So, how do I make a pickle? I soak a cucumber in a sodium chloride solution, a brine solution. All right. If I take that pickle, and you can see, put 2 forks in it. All right, I'm going to apply a high current through that pickle, and we'll just see what happens. Okay, so you can see light being formed there. Now you can see smoke too, but applying that high current through it means we're basically heating up the pickle. We're also heating up the sodium and chloride ions that are in the brine solution that are inside the pickle. And what we're doing is we're exciting those electrons within those ions and causing them to go to an excited state, fall back to a ground state, emit light. Alright, so that's one way we're causing this emission of light. We're passing a current through this pickle, causing this emission. Let's look at another example of this. So what we're going to be looking at now is a flame test. What we're going to be doing is we're going to be taking a solid salt. We're going to be putting it in a Bunsen burner flame. When that salt goes into the flame, it's going to be changed in the gas state, and then it's going to be excited even further so that the electrons inside those atoms go to an excited state, they fall back to their ground state, they emit light. So you can see there we're using sodium acetate. It's got an orange flame to it. Copper chloride, it's got kind of a green-blue flame. Boric acid, it's got a green flame. Potassium chloride is a little bit harder to see, but it's a purplish colored flame. There you see it a little bit better. So you could see within those flame tests, when we went to different compounds, we got different colors. The reason why, each of those elements is going to have a slightly different color produced when we put it inside the flame. Right, but that color is being produced by excitation of electrons inside those atoms to an excited state. They fall back down to a ground state, and we get to see the color coming out. Keep those in mind as we go through these discussions, but that's some way we can visually see these electrons in the atom, at least these electrons moving around in the atom. Now, a theory that's going to help us explain electron behavior in an atom is something called the quantum mechanical model. Right, now with the quantum mechanical model, it's going to help us to understand and predict properties of atoms that are directly related to that behavior of the electrons. For example, the light being emitted by those specific elements. Each element had its own light coming out that's related to its electrons. Other properties that are going to be involved, why some elements are metals while others are nonmetals. Why some elements gain one electron when forming an anion while others gain two. Why some elements are reactive while others are practically inert. And then other periodic trends we see in that periodic table can be explained by these properties of electrons. All right, but before we get too far into that, we'll see that a little bit later on, we need to talk about electromagnetic radiation and what that is. So with this concept of electromagnetic radiation, we have three things we need to consider. Wavelength, which is represented by that lambda, amplitude, which is represented by that A, and frequency, which is represented by a V. It actually should be kind of a Greek V or a nu, right? But a lot of times you'll see it just as this V. Don't confuse frequency with velocity. Okay, that's very, very important. So let's look at the relationships between these. I'm going to use a little simulator here. So as we're looking at the simulator, we can see a wave pattern being shown there. Now, if I change the amplitude, you can see the size of those waves get a little bit bigger. If I decrease it, they get smaller. So increase, decrease, okay? But it doesn't change what we call my wavelength. All right, my wavelength is going to be from the top of one peak to the top of one peak. That distance is one wavelength. Now, frequency is going to be how often a wavelength goes by. So it's like cycles per second is a frequency. What we're going to look at here is, though, how wavelength and frequency are related. So if I increase my wavelength, notice what happens to my frequency over here. My frequency goes down. Okay, so I get fewer wavelengths per second going by on the screen. Basically, I can see one going by there, another one going by there. If I decrease my wavelength, my frequency goes up. All right, now you can see I've got a lot more wavelengths going by in 1 second. So it's going to be important to understand this relationship between wavelength and frequency. Okay, they're inversely related. As one goes up, the other goes down. So just a quick picture of this. So wavelength, like I said, is the distance between those wavelengths tops, or we could look at the troughs here. And then how often a wavelength goes by would be frequency. And then the amplitude, we're not going to focus so much on the amplitude after this point. The amplitude you just need to recognize as a higher amplitude means it's a brighter light. Now, we saw that wavelength and frequency were inversely proportional to each other. When we're looking at this electromagnetic radiation, we can say that wavelength times frequency is going to be equal to c. c is the speed of light. Speed of light value is going to be 3.00 times 10 to the 8th meters per second. It's constant. Okay, it's always going to be that. All right, so wavelength times frequency is going to be equal to that 3 times 10 to the 8th meters per second. Now, in looking at that relationship, pay attention to the units. That means my wavelength has to be in meters. My frequency has to be in a per second. Let's talk a little bit more about electromagnetic radiation in visible light. All right, so when you think of color, white light is going to be a mixture of all the colors of visible light. Now, when we think about white light then, and it being this mixture of all these colors, it's going to be something that we call a continuous spectrum. In other words, all these colors are going to blend in with each other as we go from one color to the next. Okay, there's not going to be any stop point. They're going to slowly transition into each other. Now, if you remember basics of the colors of light, you've got the red, orange, yellow, green, blue, violet. If I take white light and shine it through a prism there, I get a rainbow. Well, that rainbow is going to involve all the colors of white light. This is a continuous spectrum because as I move from red, it transitions into an overlap between red and yellow, which is that orange. So I go from the orange to yellow, those are overlapping. As I go from the yellow to the green, those are overlapping, green to blue, and so on. Okay, it's a continuous non-stop spectrum of changing colors. Now another thing to think about when we're dealing with colors. Why do blue jeans look blue? This concept is going to be very important. When we have an object, it's going to absorb some of the wavelengths of that white light that we were talking about. It's going to reflect others. In doing that, it's going to appear to take on a certain color. So if I look at these blue jeans, there's pigments and dyes in there, which are basically organic molecules that are going to absorb certain wavelengths of light. They absorb everything but the blue color. They reflect that blue color. That's why the blue jeans look blue. It's not because they absorb blue, it's because they're reflecting blue and they're absorbing everything else. So the observed color is going to be the color reflected. Right? So if I look at this red shirt here, as the white light comes in, remember it's that mixture of all the colors of the rainbow coming in, strikes that white shirt, the red color is going to be reflected. Now, is it just strictly going to be red? No, there'll probably be a little bit of orange, but red is going to be the predominant one that's reflected. Well, let's look at another example of this and using a spectral analysis of absorbance of these different wavelengths and colors of light. Right? Well, why do leaves look green? Well, if you look here, as that rainbow comes in, what colors are going to be reflected? Well, it's going to be that green and yellow are going to be reflected. The blue and the red are going to be absorbed. Right? And you can see in this absorbance spectrum, you can see a larger absorbance in that blue area and a larger absorbance in the reddish area. So the green and yellow aren't absorbed by the leaf, they're reflected. That's why it looks green. So what happens during the fall to leaves? Well, they change color. They change to that red and orange color. Why does it happen? What's occurring? Well, as those leaves go through their biochemical changes, the components in them, the chemical compounds in them, change as well. They change to different compounds. Those different compounds now absorb at different wavelengths. So now they go to wavelengths that absorb the blue, green, and yellow region, and they don't absorb much of the red, which is why those leaves start to turn reddish in color. Okay, that's what's happening though, is a change in those chemical compounds inside the leaf. Now, let's think about electromagnetic radiation along with this concept of color. Remember, we've got that wavelength, amplitude, frequency. We're going to focus mainly on wavelength and frequency. Amplitude is just going to be how bright a light is. All right, and wavelength times frequency is going to be equal to C. Keep that in mind. That's a very important equation you're going to need to know. Those colors we saw are going to be determined by the wavelength of the light. If I look at this top one here, it has a certain wavelength associated with it. All right, probably in the 700 nanometer region, and that's associated with red. Okay, when I look at the middle one there, it's green in color. It's got a shorter wavelength, probably about the 500 nanometer region. That's why it looks green though, it's because it's got a shorter wavelength than the red. And when I go to the blue at the bottom, it's got an even shorter wavelength. So wavelength is going to decide what color we're looking at, what color we're seeing. Now also listed on here is the frequencies. All right, so you notice as the wavelengths get shorter, what happens to the frequencies? The frequencies get higher. So as we go to shorter wavelengths, we go to higher frequencies. Okay, they're inversely proportional to each other. All right, let's look at an overall picture of this, and we're going to deal with the overall electromagnetic spectrum. Keep in mind this, wavelength times frequency equals C. All right, when we look at the overall electromagnetic spectrum, we can see that the visible light, the light we can actually see, is a very small region on this scale. So if we start from the left, we go from gamma rays to X-rays, then we go to ultraviolet or UV rays. Okay, notice the ultraviolet is on the violet side of the visible region. So as we hit the visible region, we go from that violet over to the red. Once we get out of the red, what do we go into? We go into the infrared. And from the infrared, we go to microwaves, and then we get into radio waves. As we go from gamma rays to radio waves, the wavelength is increasing, which means the frequency is decreasing. One of the big things with this that you've got to recognize is when we talk about electromagnetic radiation, all of these things involve electromagnetic radiation, and they can apply to this wavelength times frequency equals C. It's not limited to just visible light, but a lot of times people use light to talk about electromagnetic radiation. Okay, so just keep that in mind. There's a lot more electromagnetic radiation out there than just visible light. All right, slightly different view of this. Notice the radio waves are now on the left, gamma waves are on the right. It's also got a frequency scale. If you look at the wavelength, it's longer on the left, smaller on the right. If you look at frequency, it's smaller on the left, larger on the right. Remember that inverse relationship between frequency and wavelength. Another thing to note that we'll get into later is we need to look at the energy of these electromagnetic radiations. The larger the wavelength, the smaller the frequency, the lower the energy. So radio waves have really low energy. Whereas if you go to the other side, to gamma rays have really high energy. Now another thing to note, a lot of times you'll see frequency reported in a hertz. Alright, well 1 hertz is equal to 1 per second. Alright, frequency is going to be that cycles per second or number of things per second. Okay, well 1 hertz is 1 thing per second, or we just represent it as 1 s to the minus 1. Okay, so hertz and s to the minus 1 are going to be interchangeable units.